Hi, 8th graders. We are going to start with 6.4 today, but before we begin, I want you to get out your bell ringer. I'm going to kind of go over the bell ringer a little bit with you, and then you're going to pause this video and finish the bell ringer, then turn it in, and then we'll continue on with the lesson in the video. So number 19 and 20, it says the vertices of a figure are given. Draw the figure and its image after dilation with the given scale factor. Identify the type of dilation. So what you're going to need to do is get some graph paper over in my paper organizer. I get the ones that have a couple of graphs on them and then staple this to that. You're going to need 2 graphs for this problem. So I'll go ahead and grab my graph. Okay, so I'm going to use this graph for number 19, and then I'll use this graph for number 20. Okay, so here's what we need to do. We need to first just draw this shape, like plot it on there, and then we need to dilate it with this scale factor and then draw its new image, okay? And don't forget, the new image will be prime, so it'll be A prime, B prime, C prime, okay? Now I want you guys to try 19 on your own. I will do 20 with you. So on number 20, first we're just gonna go ahead and start with J. J is back 8, down 4. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. Okay. And that is J. The next one is K is over 2 up. Oh, yeah. Over 2 down 4. 1, 2, 3, 4. And then I've got L, which is over 6. 1, 2, 3, 4, 5, 6. And then down 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that was L. And then M is back 8, which is in line with J right there, but then down 10, which I've learned is right there. And that is M. Okay, so I'm going to go ahead and draw that. Okay. Perfect. Okay, so that's my first image, or yeah, that's the pre-image, and now we're going to go and do the image. This one dilates with a scale factor of 1/4. Now, if I were to multiply each of these by 1/4, multiply by 1/4, it's the same thing as just dividing all of these by 4, okay? So now what I want to see is, underneath here, we're going to put J prime, K prime, L prime, and M prime. -8 divided by 4 is -2. -4 divided by 4 is -1. 2 divided by 4, that's a half. -4 divided by 2 is -4. I gotta remember what we're doing here. Yeah, okay. -4 divided by 4 is -1. All right. 6 divided by 4, that turns into 6/4, which is the same thing as 1 and 1/2, right? If I reduce this, I could take out a 2, take out a 2. I'd get 3 over 2, which then would turn into 1.5. Okay, so 1 and 1/2. Erase that for a second. Okay, so now we got -10 divided by 4. I can take 4 out of 10 twice. And if I did that, I'd have 2 left over, which is a half, right? So it'd be -2 2/4. I'm glad we're doing this one together. A lot of fractions. -8 divided by 4 is -2. -10 divided by 4, we just found out was -2 and a half. I'm going to change this one to be 2.5, just so that I can keep them all the same. Okay. Woofta, we're done. Now all I have to do is go put that on my graph. I'm going to do it in a different color for now, just so that you guys can see it better. Okay, so J prime is back 2, down 1. Back 2, down 1. So there's J prime. Now it will make sense for this to be so much tinier because we had a scale factor of 1/4. When you multiply everything by 1/4, it does get smaller, right? The next one is over a half, down 1. So there's little k. L is over 1.5, over 1.5, and then down 2.5. 2.5, oops, I think I did that one wrong, over 1.5 down 2.5. Ooh, he's gonna just be hanging out in the middle of nowhere. That was L prime. And then M prime is back to down 2.5, so this guy's gonna go down 1, 2.5 right here. L prime. Tiny. Okay. Right, and it makes sense though for that to be tiny because we multiplied by a fraction. Now this guy over here though, when you guys do 19, he shouldn't be tiny. He should start out small-ish and then get bigger because you're multiplying by a whole number, okay? All right, and then for number 21, I want you guys to remember, you have to know the sum of all these angles first, remember, before you can find your unknown. Or you could just look at it and say, if these two are the same, what do you know about these two? Okay, so pretty simple bell ringer today. But you go ahead and pause this video if you need to finish, and then put your name on it, turn it in. Now we can get started with the lesson. Okay, so the lesson today is comparing linear and non-linear functions. It is really simple. I mean, honestly, this whole chapter has been pretty easy, to be honest with you. But this one's really easy. The first thing I want to just start with is the most obvious thing here is non-linear functions don't make straight lines. So do you see that neither of these are a straight line? These would be called non-linear functions. So underneath here, I'm just going to write non-linear functions don't make straight lines. Okay? That's the whole thing. Non-linear functions are just going to be things that aren't making straight lines, okay? You don't have to learn how to graph these yet. That's what you're going to do in high school. But right now, you just get to learn that that's not a linear function. That's something else. That's a function. It's just not a linear function. But now up here, let's talk about linear functions. Linear functions are straight lines, right? But we know y equals mx plus b makes a straight line. Y equals mx makes a straight line. Y equals b makes a straight line. So here's what I want us to do. See how I color-coded green, yellow, and pink? We are going to use those to graph some lines, okay? The first one I want us to do, that's going to be highlighted in green in a second, let's do an equation. Y equals 1/2 x plus 3. How about that? Okay, I just totally made that up, but let's do it. If I said, is that a linear function? That means you could graph it and it would be a straight line. Let's go do that. Go up 3. I'm going to grab a black just so that mine's similar to what yours will look like later. Up 3, because that's the y-intercept. The slope is up 1 over 2. Up 1 over 2. Or I could go down 1, back 2. Down 1, back 2. And then go ahead and grab a ruler. Make this look really nice in your notes. Straight line, right? That is a linear function. I'm going to grab a green highlighter. I'm going to highlight my little green line right there. Okay. So, linear function makes sense. Makes y equals mx plus b, right? Okay, let's talk about y equals mx. Who's missing? The b. So what if I had an equation that looked like this? Here, I'll grab another color just so my notes look pretty for you guys. If I had y equals 1/2 x, or not even, I could even do something like this. How about y equals 3x, okay? If there is no b, that just means b is 0. So that means the y-intercept is 0. So I'm going to start right here in the center. And now the slope is up 3 over 1. Up 1, 2, 3 over 1. Up 1, 2, 3 over 1. Or I could go down 3, 1, 2, 3, back 1. 1, 2, 3, back 1. And there's my next linear equation. I'm going to go and draw my line through that the best I can. Oof, that was not very good. Let me try that again. Oh my gosh, why am I so awful at this today? Okay, well, beggars can't be choosers. That's the best I can get. I'm going to highlight that guy yellow. Okay, so if you see this type of equation, it's going to make a straight line. If you see this type of equation, it's going to make a straight line. Let's go focus on this. Who's missing on y equals b? The mx. Now the mx, the m is the slope. And we know that, for example, what if, let me grab a red real quick. What if this was y equals, I don't know, -5? That means it's going to be a straight line, a straight flat line at -5 on the y. So if I go down 5 on the y, 1, 2, 3, 4, 5, put my dot, the slope doesn't exist. So it's not up 1 over 1. Like it literally isn't even there, which means it is flat. So I can just draw a straight line right through there, okay? I'm going to go ahead and highlight him in. You guys don't have red highlighters, I don't think. No, you have pink. So I'll grab a pink and make it pretend that's red. Okay, I'm going to highlight that little guy. Okay, so here's what I want you guys to understand. All of these equations are called linear functions because they make a straight line. Whether it be going this way, going this way, going this way, they're making straight lines, okay? So now what the book is trying to teach us is, if you just looked at a graph, could you tell me if it's a linear function or not? Yeah, that should be easy. I'm hopping over to the textbook real quick. Is that a linear function? No, because it's not a line. Is this a linear function? Yes, because it's a straight line. That's literally all we're asking here. Is this a linear function? No, because it's not a straight line. Yes, it's made up of straight lines, but that's not a straight line. That's upside down V. No, that's a no. Okay, but now here's the second part of this. Could you look at a table and tell me if it is a linear function? So let's go do some of that in our notes. I have 2 examples down here. Okay, how this works. If this was a linear function out of these tables, that means I could write a y equals mx plus b equation, right? But what I need you to understand is the slope from each of these ordered pairs would be the same. So to find out if this table can make a linear function, we just have to say, hey, is the x's changing by the same number each time? And are the y's changing by the same number each time? So here's how we're going to do this in our notes. We're going to say 3 to 6, what happened? Plus 3. 6 to 9, what happened? Plus 3. 9 to 12, what happened? Plus 3. So far, so good. If these are all going by the same thing, yes, so far we're doing great. Now let's go do the y's. Y, how did 40 turn into 32? Minus 8, because 32 plus 8 would get you 40, right? Now, is it minus 8 to get here? Is 24 plus 8, 8, 9, 10, 11, 12, that'd be a 2, that'd add 1, that would be 32, right? Okay, let's check this one. Minus 8, 16, is 16 plus 8, 24? Let's see, 8 and 6 would be 14 plus 1, yeah, that'd work. So if the pattern works right here, right here, right here, right here, right here, right here, that means we're going at a constant rate, which means the line is going to be going, you know, down 8, up 3. I mean, it's going to be constant. So if you look back at these notes in the book, this one is right here. If we're going up by 3, up by 3, up by 3, down by 8, down by 8, down by 8, because it's increasing or decreasing at a constant rate, it is a linear function. So you don't even have to create a y equals mx plus b equation for me. All you have to do is see if it's going at a constant rate for all of the x's and all of the y's. This is a yes. Okay, let's go and look at the next one. Let's look at the pattern. 1 to 3 was plus 2. 3 to 5, plus 2. 5 to 7, plus 2. Okay, so far so good. 2 to 11, let me think, that'd be subtract, oh wait, no, sorry, be add. 8, 9, 10, that'd be 8, so 9. Add 9. Is this 11 plus 9 though? No, because 9 plus 11 would be 20, right? Is it not 33? If you look in the book, it shows you what the next pattern is. It's going to be 9 plus 22 gets you there. Plus 55 gets you there. Okay, so obviously this is not going up at a constant rate. It's jumping around like crazy. So would this create a straight line on a graph? No, it would not. Okay. I just gave you guys this little note right here just to help remind you that slope is the change of y's over the change of x's. I just really need you guys to remember you do the y's on top, then the x's, because you're going to need it for later. Okay, so that's part of the lesson, but there are other pieces that in the textbook that I didn't really cover, and I want to show you what I mean by that. There are other questions that are going to be like this. Which of these equations, A, B, C, or D, is a non-linear function? In other words, it's not y equals mx plus b, right? Well, if we look at A says y equals 4.7. Is that y equals mx plus b? Some kids are going to say no, but I want you to understand that just because you don't see the x, that doesn't mean it's not a linear function. It just means that the slope is 0. Like, for example, if I were to graph this, y equals 4.7, I would go up 4.7, which, is almost 5. It'd be like right there, and it'd be a straight line right through there, okay? So when you see y equals and then just a number, it actually is a linear function. It's just a flat line, okay? So A is a linear function. Let's look at B. Some kids see the pi and they get freaked out, but just think of pi as like a number. Like I could literally replace this with just like a 3 or something, and then it would still work, right? Is this y equals mx plus b? Yeah, it's just that we don't have a b, right? So y equals pi x, you could still graph that. You would just go up a pi over 1, up a pi over 1 as a slope. And I know that sounds silly, but you could do it. So is this y equals mx? Yes. So is that a linear function? Yes, which means it's not our answer because we're looking for nonlinear. Now I'm going to skip over to D for a second. If I distribute this, I would get y equals 4x minus 4. That is y equals mx plus b. So yeah, is that a linear function? Yes, it makes a straight line. Do you remember when I used to say x in the numerator? Good. X in the denominator? Bad. That's because that's not a linear function. If it was written y equals 4x over 1, that's good. We like that. That's just y equals 4x. That's a linear function. But if x is in the denominator, that changes everything. That means that this is actually y equals 4 divided by 1x. You can't just pop the x up here. He's being divided by the 4. It's a mess, okay? So is this a linear function? No. Would this make something on a graph? Yes. But will it make a straight line? No. Okay, so that is something I wanted you guys to understand is you're also going to have to take equations and find out if those equations make linear functions, which is actually stuff we've already done. Like, for example, is this y equals mx plus b? Yes, there's a 1 in the m, right? So the question is, does this equation represent a linear or a non-linear function? This would be linear. Number 5, x in the numerator, good. So this would be y equals 4/3 x. That's y equals mx. This is linear. Makes a line. Ooh, see that? We don't like squares. That makes things on the graph for sure, but they're definitely not straight lines. So because of that, that is a big sign that this is going to be non-linear. Okay? All right, that's essentially it for the lesson. That's why I thought it was pretty simple. Linear versus nonlinear, you can tell by looking at graphs, you can tell by looking at charts like that, and you can tell just by looking at equations if it's going to make a line or not, okay? So what I'm going to have you guys do now is get out your practice page, and I want you guys to finish this in class. I know you have plenty of time. Make sure you put your name on it. It says graph the data in the table and then decide whether the graph is linear or nonlinear. So plot these points, and then underneath it, tell me if it's linear or if it's non-linear, okay? 3 and 4, are these linear or non-linear? Pretty easy, right? 5 says, the table shows the area of a square with a side length of x. Does the table represent a linear or a non-linear function? So what they're saying is, every time we increase the side length, the area increases of this square, right? All you have to do is say, does the pattern continue on in a constant rate? If it does, then good for us. It's a linear function. If it doesn't, then it's a nonlinear function. All right, guys, lots of things to do today. First, you had to do your bell ringer, then you had to fill out notes with me, then you have to do your practice page. When you are finished, feel free to work on some missing work or read a book. All right, bye, guys.